Hello everyone. This is a review for exam 2, selected problems. I basically just took problems from our review assignment and we'll solve them here for you. You should probably have your cheat sheet ready for the exam. So here's the familiar formulas for the derivatives of the inverse trigs as well as the antiderivatives that result in the inverse trigs. So I have those handy as we work through this, unless you've memorized them, of course, which would be a good thing. But looking at our first problem, okay, the exam is purely mechanical, like we talked about. Here we're just finding derivatives. So we should recognize that the inverse secant of 5t is a function of t, and t squared obviously a function of t. So treat them as u and v respectively, and we're going to need the product rule. And so therefore, by the product rule, g prime of t would be our first factor, t squared, derivative of the second. Okay, so now is where you're going to need your formula sheet, unless you've memorized it, for the derivative of the inverse secant. You can check the formula there. And it is in the denominator, the absolute value of u. The u is 5t, and then times the square root of u squared minus 1, and u again is 5t, but that has to be squared, and then minus 1 under the radical. And in the numerator, du dx, the derivative of u being 5t is just 5. So there's the first part of the product rule. That is the first times the derivative of the second, or uv prime, and now we need the rest of it, plus v inverse secant of 5t, and then times u prime, and the derivative of t squared, just simply 2t to the first, or 2t. So that finishes up the product rule. There's plus or v in our u prime. So g prime of t is... You could actually cancel these 5s. You don't have to, you could leave them. But you can't cancel the t's. You have to leave the t's because the absolute value can only cancel constants. So I'd have to leave it as t squared over the absolute value of t, and then times the square root of. Make sure you square that binomial. That is the 5t that's being squared. Not binomial, monomial, excuse me. But square the 5t to get 25t squared, then minus the 1, and plus, let's just bring the 2t out in front of the inverse secant of 5t. Okay, so I'm going to try to mix things up, give you situations. Obviously, they're going to involve inverse trigs, but I'm going to try to involve exponentials, logs, whatever other functions. So here we see some exponentials, but inverse cotangent of e to the 3x, that's a function of x. E to the 3x, a function of x. Treat them as u and v again, and it looks like we need the product. So by the product rule, h prime of t, first factor, e to the 3t, derivative of the second. Okay, once again, look at your formula sheet. This one's for the inverse cotangent, so it's a minus, and then a 1 plus u squared in denominator, and du dx in the numerator. So 1 plus the u in this case is the e to the 3t here, that's the argument of the inverse cotangent, and that has to be squared, and then in the numerator, the derivative of that, e to the 3t, which is e to the 3t times 3. So that again is just the first part of the product rule. That is u and v prime. And now we need plus v, the inverse cotangent of e to the 3t, and then times u prime. And that's the derivative of this e to the 3t, which would be e to the 3t times 3. And there's our vu prime to finish the product rule. And so then Just making it look a little bit better. Okay, in the denominator we have 1 plus. Here we're taking a power raised to a power. We have to multiply the exponents. So 1 plus e to the 6t. In the numerator we have the 3. And then here we're actually multiplying common bases. So we're adding the exponents. And we get e to the 6t there as well. And then for the second term, let's bring the 3 e to the 3t out in front of the inverse cotangent of the e to the 3t. Okay, so there's typical situations involving the product. The next example should be obviously obvious that it's a quotient. So function of x in the numerator, function of x in the denominator. So by the quotient rule, and draw a big fraction, we take the denominator, inverse sine of 5x, derivative of the numerator, derivative of e to the 2x, that's our e to the u formula again, so e to the 2x recopied, but then times 2, the derivative of the power on the base of e. So there's denominator, derivative of numerator, now minus numerator, e to the 2x, and then times the derivative of the denominator. Okay, now we need our formula for the inverse sine of 5x. So again, check the formula sheet if you need to. It's square root of 1 minus u squared in the denominator. So square root of 1 minus the u here is the 5x. But that has to be squared. And in the numerator, the derivative of 5x, which is 5. And that's all over that denominator, inverse sine of 5x as a quantity squared. And so, with regards to the quotient rule, there's vu prime minus uv prime all over v squared. Now, I just realized in the last example, I actually did make a mistake. Cotangent inverse, its derivative is negative. So make sure you slide that little negative in there. And it carries on along to here. So that's just an example of what a 1-point error would look like. Okay, but continuing with this one. Okay, in the next step, I'm really not going to do much. I'm kind of just going to regroup. I'm going to recopy the inverse sine of 5x that's being squared in the denominator. The numerator, I'll write this first term as 2e to the 2x. Inverse sine of 5x. And I'll write the second term as a single fraction minus, in the denominator, the square root of 1 minus. Make sure you square that 5x to get 25x squared, and then I'll write that as 5e to the 2x. Okay, but here you'll get the majority of credit if you stop there. But this is the complex fraction that we're used to seeing, where I feel the most efficient way. You could simplify this any way you want, but I feel the most efficient way multiplied by the least common denominator between all of the terms, which in this case is that square root. And so that will clear the fractions for us and get the best looking answer at this point. Essentially what happens in the denominator of the fraction is this inverse sine of 5x that's being squared is just now joined by the square root of 1 minus 25x squared. And in the numerator, that 1 minus 25x squared radical needs to be distributed. And so multiply by each of the terms in the numerator. And when we multiply by the first term, we basically just have to decide where to include it as a factor. And I think I'll just put it in the end here. But then when we multiply that by the second term, we see why we did it. That's the reason why we multiplied. So we get the cancellation, and you just get the numerator 5e to the 2x. Okay, so there's an example of the quotient rule. So be prepared to clear fractions like we had to there. Hopefully letter F you'll recognize is a function of x raised to a power. Call it u to the n. General power is what I like to call it. But if you call it the chain rule, that's fine as well. So f prime of x here, bring down the 6. Same function recopied. 1 minus inverse sine of 5x, power 1 less than 6 is 5. And then the derivative of the inside. And the derivative of the inside, term by term. Derivative of 1 is 0. Okay, let me not forget that negative. And then the derivative of the inverse sine of 5x. Again, your formula sheet. Square root of 1 minus u squared in the denominator. So square root of 1 minus u is the 5x. Needs to be squared. And in the numerator, the derivative of that argument, 5x, which is 5. So, with respect to the general power rule, there's nu to the n minus 1 and du dx. So then making this look better, f prime of x would be, I suppose you could write it in a variety of ways. I'm just going to make it a single fraction of the square root of the 1 minus 25x squared in the denominator. In the numerator, I'll multiply the negative 5 and the 6 to get negative 30. And then we've got the 1 minus inverse sine of 5x as a quantity to the 5th. Okay, and then looks like another one that's a power. That is immediately, no matter what. Oh, I guess there's a little mistake in here. This should not be f of t. This should be f of x, because this is a function of x. But in any event, first move no matter what, get rid of the radical. So 1 plus inverse cosine of 4x. Okay, that's a square root, so 1/2 power. Be prepared for other roots, like cube roots, 4th roots, 5th roots, and the odd root might come into play, just to keep you on your toes. But again, it's the general power, chain, u to the n, whatever you want to call it. Okay, so f prime of x is, right, once again, don't differentiate too early. You're going to swing down the 1/2, recopy that same function, 1 plus inverse cosine 4x, power 1 less than 1/2, negative 1/2, and then the derivative of the inside. And term by term, the derivative of the inner function, derivative of 1 is 0 for inverse cosine. Same as inverse sine, square root of 1 minus u squared in the denominator, u being 4x. Only difference is that it's a minus, and then the derivative of, in this case, the 4x, which is 4 in the numerator. So, again, with respect to the general power rule, there's nu to the n minus 1 and our du dx. Okay, here I have to bring down the quantity here that's raised to the negative 1/2. So f prime of x would be, I'd probably also cancel the 2 with the negative 4. So it looks like the only thing in the numerator is the negative 2. And then we've got this quantity, 1 plus inverse cosine of 4x shifted to the denominator. Now raised to the positive 1/2, and that joins the square root of 1 minus, make sure you square the 4x there to get 16x squared. And if you wanted to be fancy, you could put the whole thing under a square root in the denominator, because the 1/2 power is a square root. Okay, moving on to the next page. So there's a good sample of the derivatives. You're going to get one product, one quotient, one power. And then we go to integrals that result in the inverse trig functions. And guaranteed is going to be one of each type, similar to these. First one's the classic situation. I'm not going to argue formally, I'll just do it verbally. The reason why this does not fit u to the n, because remember, whenever we see a fraction, it's either du over u or u to the n. U to the n if it's a power in the denominator, du over u if it's not a power. So this would be u to the n, but if we took u to be that entire quantity under the radical, its derivative 72x. We don't have an x in the numerator, we've got an x in the denominator. So we turn our attention to the integrals that result in the inverse trig functions. And remember, to get a start on the problem, all you have to do is classify the terms that are under the radical or in the denominator without the radical, because there's only two choices. Look at all the formulas. Look at the three formulas we have. It's either square root in the denominator and either of these, no square root in the denominator and the inverse tangent. But you classify them with respect to a and u, where a is the a squared and u squared, I should say, where a is the real number and u is the function of x. But you want to classify them with respect to a squared and u squared. So this would fit the form for u squared minus a squared. Now, before we continue, if you want some reassurance, look at the formulas, make sure we have one with that, and we do. There's the squared u squared minus a squared there. We're going to have to talk about the u being satisfied out in front, but we know we're headed in the right direction. And now we'll start the process. So off to the side, I'll pick a squared. That's going to be 49. U squared of 36x squared. Remember, a and u are never negative. A squared and u squared are never negative. The minus is part of the formula. Then we make the concession and take the principal or positive square root. So a and u are never negative as well. In this case, a is 7, u is 6x. This is still u substitution, so you still have to calculate your du. That's 6dx. And we'll modify to get 1/6 du is dx. Now, I'm going to do it this way. I'll call this 1 dx. I'll satisfy that, because that represents 1/6 du. But we have to make sure that we satisfy the u that is out in front of the radical in the formula. So in the formula, we see that we have a u out in front of the radical. And that u, in our case, is 6x. So therefore, we need a 6 in front of the x. So I like the brute force concept. I'm just going to slide a 6 in there. And to compensate, I'll slide a 6 up top. And now that 6x that's in the denominator, that whole thing makes up my u. So now everything's accounted for. Ready for the change of variables. But I have the black 6 and then times the red 1/6. And now the remaining change of variables gives us the integral of du over u and the square root of u squared minus a squared. So if you have to look at the formula, well, these 6's cancel. That integrates to be 1 over a, inverse secant, absolute value of u over a, at our constant at that point. And back substitute, a was 7, so 1/7 inverse secant absolute value of u was 6x over a, which is 7, plus or constant. Okay, so guaranteed something very similar to that. Okay, situation here, if it's going to fit, again, I'm just going to argue quickly why it's not u to the n, and it would be u to the n because of power. Take u to be the entire quantity under the radical, knowing du needs to be satisfied. Its derivative is negative 6x to the 5th. We don't have that, we only have an x squared. So once we discern that it's not one of the basic two, u to the n or du over u, classify the terms in the denominator. One is the constant, so we'll call it a squared, minus a part of the formula. X to the 6th is the variable, so we'll call that u squared. And then if you want some reassurance before you continue, look at the formula sheet, and you see that we do have something of that form, square root of a squared minus u squared in the denominator, that results in the inverse sign of u over a. So following through with the particulars, a squared will be 1, u squared x to the 6th. Okay, that means a is 1. Okay, if u squared is x to the 6th, u is just x cubed. Remember, the easy trick is just divide the exponent by 2, because you're really raising to the 1/2 power, and then multiplying exponents. If you multiply by 1/2, that's the same as dividing by 2. So our du still needs to be calculated. That's 3x squared dx in this case. And then we modify routinely, so 1/3 du is x squared dx. And if we go back to the integral, we've already established the denominator. If we look at what's left in the numerator, we see x squared dx, compare it to our du, and a match just modified by the 1/3. So we're ready for a change of variables. We'll bring out the 1/3 because everything is accounted for, notice. And upon change of variables, we have 1/3 integral and then du over square root of a squared minus u squared. Alright, once again, look at your formula sheet if you need to. That integrates to be just the inverse sign of u over a, plus or constant, and then back substituting 1/3 inverse sign. U was x cubed over a was 1, so just inverse sign of x cubed, let's say, and then plus or constant. Okay, now in the next one, we got some exponentials involved. There's no radical in the denominator, so if this were to fit a basic form, it would be du over u. But that's not going to work because the derivative of the denominator is e to the 6x times 6. We don't have e to the 6x. We only have e to the 3x. So we go again, to get a start on the problem, just simply classify the terms in the denominator with regards to a squared and u squared. So in this case, a squared plus u squared. And off to the side, start the process. A squared is 25. U squared, e to the 6x. That means a is 5. And u would be, again, the easiest way, just take half of what the exponent is. So u to the 3x. Du needs to be satisfied. Put yourself in the differentiation mode here. The derivative of e to the u is e to the u, so e to the 3x times the derivative of the power on the base of e, so times 3. Differential dx as well. And we modify by the 3, so 1/3 du is e to the 3x dx. Alright, looking back at the integral, I guess I forgot to mention, for reassurance, if you want, look at the formula sheet. And here you can see we do have 1 with a squared plus u squared in the denominator. So that's what we're shooting for. Look at the leftovers in the numerator, e to the 3x combined with the differential dx. Compare them to our du here. And we see they match. just modified by the 1/3. Okay, so we're ready for the change of variables. Bring out the 1/3 integral upon the change of variables, du over a squared plus u squared. Then integrate the 1/3 tags along. Look at the formula sheet if you need to. Integrates to be 1 over a inverse tangent of u over a. Add our constant at that point. And now we'll back substitute. A was 5, so 1/3 times 1/5, 1/15th. And then the inverse tangent of u was e to the 3x over e, which is 5. And then plus our constant. Okay, the next example is a situation that involves a definite integral. And it's easy to see here that du over u doesn't work because the derivative of the denominator is 2x and we don't have the 2 in the numerator to help satisfy the du. Now, in this case, you could classify everything like normal. You could say this is a squared plus u squared. But there's really no need to show this because if a squared is 1 and u squared is x squared, then a is 1, u is x, and the du is just simply 1 dx. So there's really no modification by a constant multiple necessary here. And the 1 dx makes up the du. And if you do make a change of variables, so that 1 dx makes up the du identically, if you do make a change of variables, it's kind of silly because all you're doing is replacing the x's by u's. So if you look at the formula sheet, and we see that this form of du over a squared plus u squared when a is 1 and when u is x would take the form of 1 over 1 plus x squared. And that would result in 1 over a, or 1 over 1, inverse tangent of x over 1. Or in other words, just the inverse tangent of x. So you can go through the formal u substitution if you need to, but this is actually a good integral to memorize, just the basic 1 over 1 plus x squared. So I'm just going to say that this is the inverse tangent of x, evaluated from negative radical 3 to 1. Okay, and then upper limit goes in, so inverse tangent of 1 minus lower limit goes in, inverse tangent of negative radical 3. Okay, and now we need to do some side work and evaluate each of these. So here's the way I go about it. You could use your calculator, whatever you want to do, but I'm going to show it the formal way. So let y, and then my results I'm just going to put in here to finish it off. If we let y equals inverse tangent of 1, by definition, the tangent of y is 1. Make that a fraction, 1 over 1. Go to the Cartesian system. Based on the fact that the tangent is a positive value here. Remember, all students take calculus. We'd be in quadrant 1 or quadrant 3. But the range of the inverse tangent is from negative pi over 2 to pi over 2. And that, as an interval, represents quadrants 1 and 4. Or some people say quadrant 4 and quadrant 1. But in any event, that leads us to the fact that we could eliminate the angle in quadrant 3. And so just working off the angle in quadrant 1, pick a point, drop a perpendicular. There's a reference triangle. That's our angle y. Tangent opposite 1 over adjacent 1. Immediately that rings a bell. That's the square root of 2. And y must be 45 degrees. And you convert that by multiplying by pi over 180 to get pi over 4. So inverse tangent of 1 is pi over 4, and then we have minus the inverse tangent of negative radical 3. And for that, it's pretty much the same routine. Let y equals inverse tangent of negative square root of 3. By definition, tangent of y would be negative radical 3. Again, we'll make that a fraction, negative radical 3 over 1. It represents opposite over adjacent again. Okay, here we could kind of shortcut the argument, because in the last case, tangent was positive. The tangent of our angle was a positive number, so we decided 1 or 3. But now, since the tangent of our angle is a negative number, it would be 2 or 4. And then based on the range, once again, we'd eliminate the 1 in quadrant 2. So, working off the angle in quadrant 4, there's our point, drop a perpendicular. Okay, the angle y is measured off the x-axis, so that's going to be it. But it will actually be negative, because we'll be measuring it in the clockwise direction. And then opposite side, negative radical 3, adjacent side 1. Immediately you should recognize that as our 30, 60, 90, where the hypotenuse is 2. And so the angle y being opposite of radical 3 must be 60 degrees. But it's going to be a negative because we're measuring it, again, counterclockwise, or clockwise. So unit conversion factor is negative pi over 3. So back here we got pi over 4 minus a minus pi over 3. Common denominator of 12. 3 pi over 12. Minus minus would be plus. Common denominator 12 again, 4 pi over 12. And so we get 7 pi over 12. Alright, and we go one more example. And then we'll save integration by parts for a full another part to this review. But the last example concerning inverse trigs is completing the square. And so, recall the way I told you to go about this was that in order to complete the square, the leading coefficient has to be a 1. If it's not, I told you what I would do was design it so that it would be a whole number factor of the linear term. So we're just focusing on the first 2 terms of the quadratic here. And we're going to factor a 4. We'd be left with x squared minus 2x. And leave a little space, close up the parentheses, push the plus 85 off to the side, go so far as to leave another space to bookkeep, and compensate for whatever we do inside the parentheses to complete the square, and then we have 1 over all of that with respect to x. So that's the initial setup. Now the magic number that completes the square. Remember, we take 1/2 of the linear coefficient, negative 2 in this case, which is negative 1, and then we square it, so we get plus 1. But if I add 1 inside the parentheses here, I've really added more than just 1, because don't forget we had factored out that 4. So I've really added 4. And to compensate, we would have to add the opposite or subtract 4. Alright, now the trinomial that we created, this trinomial here, recalls what we call the perfect square trinomial, and it's expressible as a binomial square. But one thing you have to make sure you realize is this 4 is attached to that. So it's 4 and then the binomial squared. First term of the binomial is always going to be x. Second term of the binomial, whatever half the linear coefficient was before we squared it, sign included, if you want to look over here, -1. And then we combine the constant terms, and 85 minus 4 is 81. And then we have 1 over all of that with respect to x. Alright, so now we can classify the denominator. Remember, u squared is the variable, so this will be u squared plus a squared. And that fits the form. In fact, when we went over this in class, here's your formula sheet. I even rewrote right below the a squared plus u squared version, the u squared plus a squared version, which is identical, results in the inverse tangent, and is identical, of course, because addition is commutative. Okay, so off to the side. Follow through with the particulars. A squared is 81. U squared would be 4 times that binomial squared. That means that a is 9. U would be the square root of 4, which is 2, and that times the square root of that binomial squared is just the binomial. Remember, it's still u substitution, so du must be satisfied. The 2 tags along, derivative of x is 1. In differential, and derivative of 1, of course, is 0, so in differential form, du would be 2 times dx. Now, if you can't see that, because for some reason, maybe the parentheses are bothering you, distribute the 2x to get 2x plus 2 in this case. I'm sorry, 2x minus 2. I brought over a plus 1, but that should have been a -1. So please make sure you make that correction. So it's x minus 1 is the quantity squared, which would make that 2x minus 2. So if you have to distribute and then calculate the differential du, that's fine. But no matter how you get there at this point, we modify. So 1/2 du is the differential dx. And so if we look at what's left over in the integrand, 1 combined with the differential dx, that's 1 dx, or just dx, and it matches our du, just modified by the 1/2. So we have all the variables accounted for. Bring out the 1/2, change the variables. There's du over square root of, oh, there's no square root, I'm sorry. So it's just du over, and then we have u squared plus a squared. And remember, that's the same as a squared plus u squared, which integrates to be 1 over a, inverse tangent of u over a at our constant. I'll just finish off to the right here. A was 9, so 1/2 times 1/9, 1/18. And then we have the inverse tangent of u. I'm going to put back the quantity 2 times the binomial quantity x minus 1 over a, which is 9. Both are constant. But if you put back 2x minus 2 as the argument in the numerator of the inverse tangent there, that would be fine as well. Okay, so that's the First half of the exam, a little bit more than first half in terms of the points. I think that is a total of 52 points, if I remember correctly, but in any event, it's over 50 points, what we just went over. So we'll come back for the rest of the exam, which is all integration by parts, and that's about 40 some odd, close to 50 points on that. So we'll see you for part 2 when you're ready.